Okay, hi everyone. So our discussion would be about the circulation of the atmosphere. We are going to explain the different factors which affect that circulation or movement of air in the atmosphere. Okay, so let's start. So you can see here the different circulations in the atmosphere. So you have here the microscale. The coverage will be from 0 to 1 kilometers. We have the mesoscale. The coverage will be from 1 kilometer to 10 kilometers, or from 1 kilometer to 1,000 kilometers. And then we have the macro scale, which is from or ranging from 1,000 kilometers to 40,000 kilometers. Then you can also see there the different lifespans of this circulation in the atmosphere. For example, we have wind gust, the microburst, and the dust devils, which are considered to be microscale. They are ranging from seconds to minutes. And then we have, in the mesoscale, we have tornadoes and thunderstorms, which can last 2 minutes to hours. And then we also have local winds like land breeze. Then we also have local winds like land breeze, sea breeze, and then that could last 2 hours or even 2 days. Then we also have the macro scale. This involves the synoptic scale, the weather map scale, and then the planetary scale. Some examples are mid-latitude cyclones, anticyclones, and hurricanes. And then we also have the waves in the westerlies and trade winds. So those are the different classifications of the circulation in the atmosphere. So let us have them one by one. For the small and large scale circulation, we have the microscale winds. They are considered to be the smallest scale of air motion. They are small and chaotic winds which can last for seconds or at most minutes. And then, as I have mentioned, we also have the mesoscale. It's the middle-sized phenomena. Usually, they are 100 kilometers across. So that would be the size or the coverage of the wind. And it can last for several minutes to hours. Examples are thunderstorms, tornadoes, land and sea breeze, mountain and valley breezes or valley winds. Okay. So next, we also have the macro scale. This one is the largest wind pattern. Examples are westerlies and trade winds. The examples are synoptic scale wind system, mid-latitude cyclones, and also anticyclones. We also have the tropical storms and hurricanes as examples under the macro scale winds. Then for the microscale, we have these examples. We have the eddy, the wind shear, and the turbulence. So let's discuss them one by one. Eddy is a whirl of air caused by winds striking a solid object. So as long as you can see a small whirl of air, that is already considered as eddy. Okay, we also have this, a wind shear, a change in wind speed or direction over the distance. Then wind shear can sometimes be observed by watching the movement of clouds at different latitudes. So you will be able to observe wind shear. And then the next one will be turbulence. This is an irregular or disturbed flow that creates eddies and also wind gusts. So you can see here an illustration of the microscale. As long as there would be surface obstructions, slow surface winds, which due to viscosity creates eddies. So as I have mentioned, they are small whirls of air. Then whirling winds in a much thicker layer. So you can see there around the corner of the house, at the edge of the house, you can find small eddies. And then we have a weak flow. It's just a slow moving air, but since there are edges, so you can have here the small eddies surrounding those particular edges. Now we also have the desert winds, or known as dust devils. They are surface-based cyclones. This is a result of an absolutely unstable atmosphere. If we will review stability and unstable atmosphere, what do we mean by unstable? That means that the air continuously rises. So that is a characteristic of unstable air. So it's very hot in the desert. So the land is heated, and that particular air over the land, of course, will rise. So if there is a continuous rising of air or of hot air, that could be considered as unstable. So there could be dust devils. They are usually found in deserts. So we also have under the mesoscale, we have the thermal circulation. They are brought on by changes in air temperature, in which, as we have mentioned, warm air always rises and then cold air sinks. So it creates thermal circulation. From the term thermal circulation is because of the temperature of the layers of air. So we can have here some examples. We have sea breeze. So you can see the circulation of air here. During daytime, as we have mentioned from the previous discussions, we have higher specific heat capacity for water. So it will be heated at slower rate compared to land. The land will be heated at a faster rate. So you have hot layer of air over the land. So that means that will create, that will rise. So the layer of air, the hot air will rise, creating lower pressure area. So of course, if there's a lower pressure area, if somewhere in that area there's a high pressure, then that means that the air will move from the higher pressure to the lower pressure area. So we have, coming from the water, the air will flow towards the land. So that's why during daytime, we have this what we call sea breeze. From the term sea breeze, the air is coming from the sea. Okay, so that is another thermal circulation of air. And then during nighttime, what happens? We have the land breeze. What happens this time? Since water has high specific heat capacity, it has this tendency to retain the heat or the thermal energy for a longer period of time. That's why during nighttime, you can feel that the water is still hot compared to the land. The land easily gets cold compared to water. So during nighttime, we have warmer air over the water. And we have mentioned that warm air rises. That will create lower pressure area. So somewhere in the land, there's a higher pressure area. So the wind now is flowing from the higher pressure area to lower pressure area. So that means it's coming from the land towards the sea. That's why it is known to be land breeze. So the air is coming from the land. Okay, and that happens during nighttime. Okay, then another example here is the valley breeze. During the day, air above the mountain slopes is heated and rises, creating a valley breeze. So warm air rising. If there's always warm air rising, that means it's creating a lower pressure area. So area from the other parts will go towards that. So you can see here in the illustration, we have cool sinking air. The cold air in the middle sinks. Then we have the valley breeze because warm air rises. So the wind is coming from the valley. Okay, next, we also have here the mountain breeze. So what happens here at nighttime, air above the mountain slopes cools rapidly. So during nighttime, it can radiate its energy rapidly and drains into the warm valley below, creating a mountain breeze. So what happens now? We have the cold air sinking in the mountains, or coming from the mountains, we have the cold air sinking. And then in the valley, we have the warm air rising. Okay, so we have here, the air now is coming from the mountains. That's why it's known to be mountain breeze. Okay, so next would be the katabatic winds. So you can see here in the illustration, we have air is cooled in the ice surface. And then there's a pressure gradient force. So that means it's the direction of the pressure. And then you have here the force of gravity causes dense air to descend slope. And then we have here the katabatic winds. So let's take a look at the next illustration. You have high pressure. It has cool, dense, dry air. But here, we have an area of warm, less dense, moist air, which is a low pressure area. And then the pressure gradient and the gravity force the air down the slope. So there are the two factors affecting katabatic winds. One would be the pressure gradient. Since there is a difference in air pressure, we have higher pressure area and lower pressure area. And then also, since it's elevated, there's a factor of gravitational force pulling the wind downward. So that is the katabatic winds. So it happens during winter. Okay, katabatic winds happen during winter and then originate when cold dense air situated over a highland area begins to move. As the cold air descends, so as it moves downward, it is channeled into narrow valleys where it acquires velocity capable of great destruction. So because of that pressure gradient and also because of gravitational force, since malakas yung pwersa pulling it downward, so it can actually have great velocity as it moves in a narrow valleys. And then, if you're also going to compare it with, let's say you have a hose or you have a water hose, and then you try to have the opening of the hole smaller, so you can see there that the water will be moving very fast. So if you have wind and then it is squeezed into narrow valleys, so it will acquire velocity, it will move fast, okay, or it will move very fast, which can even cause destruction. So that is katabatic wind. Any downslope wind typically stronger than mountain. It is a technical name used for drainage wind. And also wind that carries cold, high-density air from a higher elevation down a slope under the force of gravity. Again, there are two forces. We have the pressure and gravitational force affecting the winds, resulting to katabatic winds. Okay, another one, we have the Chinook wind. So you can see here, where does this one happen? It happens in the leeward. So you can see here different altitudes. We have strong wind here. And then it will move down the slope. Okay. Then you have here warm, dry air. Now, what happens here, as it moves downward, there is an adiabatic. We have here an adiabatic wherein no heat is added or removed from the system. But because it is now exposed to higher pressure area, so there's already compression and it begins to have higher temperature and it is warmed. Okay, so that is Chinook. For Chinook, warm, dry winds move down the slopes of the mountains. So it is created when a strong pressure gradient develops in a mountainous region. And then as the air descends the leeward slopes of the mountains, it is heated adiabatically. Okay, so again, the factor affecting it would be the pressure or the strong pressure gradient. Okay, next. Chinook wind is also known as the snow eater. And condensation may have occurred as the air ascended the windward side. So when it condenses, that means that coming from the gas to liquid, it will release latent heat. So it will be cooled. And then the air descending the leeward, but on the other side, we have the air descending the leeward side, will be warmer and drier. And then Chinook winds have been known to melt more than a foot of snow in a day. So because it is warmed, as it moves downward, it becomes warm because of adiabatic, and then there is compression. Okay, so that's why it is able to melt snow. Okay, next, we also have this general atmospheric circulation. When winds throughout the world are averaged over time, the local patterns vanish and you are left with the global scale. So we look into the small scale, but of course we have to look into the general atmospheric circulation or the general movement of air. Now, what is the cause of that? As we have mentioned before, we have the unequal heating of the Earth's surface. We have unequal heating because of the tilting of the Earth, because the Earth is spherical. So, at the equator, it's heated the most. And then as you move down the poles, nababawasan yung heating. And then, of course, also, we have an unequal heating because of the land surfaces and the water surfaces. Since they have different specific heat capacities, so they will be heated at a different rates. Then also, the effect of that would be the atmospheric heat transport. Okay, since there would be imbalance in the temperature, there would be imbalance in the pressure, therefore air will move. Okay. We have these models. We have the single cell circulation model and then the 3-cell circulation model. Let's take a look at these different circulation models. For single cell circulation model, we have certain assumptions that the Earth is uniformly covered with water. Therefore, we will assume that the specific heat will be the same because they are uniformly covered with water. And then the sun is always directly over the equator and there are no seasons. We have not considered here the tilting of the Earth. But in reality, we have mentioned before that the Earth is tilted and that will result to different seasons. But these are the assumptions of this model. Another assumption is that the Earth does not rotate. That is for single-cell circulation model. Okay, let's take a look at this illustration. This shows the single-cell circulation model. The one who defined this one is George Hadley in 1735. There is large temperature contrast between the poles and the equator, creating a large convection cell in the northern and southern hemisphere. So you can see here, as I have mentioned, the Earth is bulging at the center. So we have here the equator is at a higher temperature compared to the poles. So we have here higher temperature, it's hot, and then colder temperature above in the northern hemisphere, and there's also colder temperature in the southern hemisphere. The movement would always be so there will be a convection cell from higher temperature to lower temperature. So there is a convection cell in the northern hemisphere. There is also another convection cell from higher temperature to the lower temperature here in the southern hemisphere. Okay, so that is about the single cell circulation model. So that's how the circulation of the atmosphere or of the air is described. A thermally driven convection cell in each hemisphere, where hot tropics produce belt of low pressure in the equator and cold poles produce areas of high pressure. So again, warm air here. So that warm air will rise, creating lower pressure area. And then we have, from the cold area, we have higher pressure. That's why, again, from lower pressure we have a movement of the air from higher pressure, and the cold wind coming from the pole, North Pole, will move towards the equator because there is the rising of air in the equator. Okay, so that is the single cell circulation model. Warm equatorial air rises, as I have mentioned, until it reaches the tropopause, where it spreads toward the poles. So we have the troposphere, and then at the end of the troposphere, we have the tropopause, where the air now will spread towards the poles. The upper level flow reaches the poles, where the cooling causes it to sink, and it spread out at the surface as equatorward moving winds. Then as this cold polar air approaches the equator, it is reheated and rises again. So again, it is circulated in the concept wherein at the equator it's warm. It's warmer compared to the poles. Therefore, at the equator, warm air will rise. And then the cold air coming from the poles will be moving towards that region of lower pressure area. So the cold air coming from the poles will move towards the equator. That's why we have here the equatorward moving winds. And then the cycle repeats. Okay. The next would be the three-cell circulation model. Kanina, we only have one single cell. We only have North Hemisphere and South Hemisphere. But looking at this circulation model, we have now three cells. We have the polar cells, we have the feral cell, and then we also have the Hadley cell. If we allow the uniform Earth to spin, a three-cell model develops that is a close approximation to the real atmosphere. In the first model that we had, there's no rotation of the Earth. But in the three-cell model, we now have considered the spinning or the rotation of the Earth and how it will affect the circulation in the atmosphere. Okay, so now we have here the three-cell circulation model. From the term three cells, we have here the Hadley cell, the feral cell, and also the polar cells. Okay, in the Hadley cells, from the equator, warm air rises, and as it moves aloft, it releases latent heat. So that is the power, or that is the thermal energy generating the Hadley cell. Then if it's already aloft, there's already radiation cooling of the layer of air. If there's already cooling, then there will be a cold air, which will then sink. Okay, again, from the equator, warm air rises, and then there will be latent heat released. So there will be cooling also, radiation cooling, and that layer of air will sink. So that is the movement in the Hadley cell. So you can see here from 0 to positive 30 degree latitude, we have the northeast trade winds. So that is the northeast trade winds. The name is from where the wind is generated. So that is coming from northeast, then towards the pole or towards the equator. And then in the southern hemisphere, we have here coming from the southeast towards the equator. Okay, in the Hadley cell also, as it moves downward or during the descent of the layer of air, there's already the decrease in the relative humidity of air. So this mostly is found in the deserts or in the tropical deserts where the air is dry, okay, because the relative humidity has decreased. And the trade winds also, the term trade winds is coming from the trading of goods. So it is used by the sailboat so that they can trade goods from Europe to North America. That's why it's that's why we use the term trade winds. Next. Okay, to summarize, the Hadley cell we have here in the zones between the equator and roughly 30 degree, the circulation is the Hadley model. As the flow aloft moves poleward, the air begins to subside. As we have mentioned, the cold air sinks. As the upper level flow moves from equator, radiation cooling also becomes dominant. And then the cold air sinks. And also, for this one, if the air is moving away from the equator, there is an increase in the effect of the Coriolis force or in the deflection of the wind, okay? So next. Okay, looking at this illustration, we have the idealized zonal pressure belts. The equatorial low, that is the warm air rising branch of Hadley cells, having low pressure. So you have here at the center at 0 degrees, we have the equatorial low, where the area or the pressure is low. Okay, where the pressure is low, it is where trade winds converge. So you can see here the trade winds coming from the north hemisphere and then the trade winds coming from the southern hemisphere. So this one is known as the intertropical convergence zone. Then you have here the subtropical highs at this layer at around 30 degree in belts about 20 to 35 degree latitude. In this zone, a subsiding air column produces weather that is normally warm and dry. So as I have mentioned, it is where tropical deserts are located. We also have here the subpolar low. Another low pressure region is situated at about 50 to 60 degree latitude. So let's take a look at the illustration. We have here the subpolar low in the northern hemisphere, and we also have the subpolar low in the southern hemisphere. Then as a subpolar low, it's where westerlies and polar easterlies meet. Okay, so you can see here the feral cell, we have the westerlies. Okay, in westerlies, as you move at a higher altitude, it will be moving very fast, or it will be moving faster and faster. Then next to the feral cell, which is located at 30 degree to 60 degree latitude, we now have the polar cell, so which is above 60 degree latitude. So what happens in the polar cell? It is generated by the subsidence of the cold air, which is moving poleward, okay? As the air moves poleward, so that is cold air, and then it sinks. So that generates the polar cell or the movement in the polar cell. So you have here the polar easterlies. So you can see here at one point, so in the subpolar low where easterlies and westerlies meet, we have here the creation of polar fronts. And that area would be where the stormy weather occurs, okay? Where the polar easterlies and westerlies meet and where the polar fronts are generated. Okay, we have again subpolar low, another low pressure region situated 50 degree to 60 degree latitude. It is where the polar easterlies and westerlies meet. Okay, this zone is responsible for the stormy weather. And then we also have the polar highs where the polar easterlies originate. Polar highs exhibit high surface pressure because of the surface cooling. Okay, again, so we have three cells for the circulation or the general circulation of the atmosphere. So you can see here in the map, you have a subtropical area. We have high pressure area here. Then another subtropical area, we're in high pressure here. And then for the equator, we have low pressure. Polar cell and Hadley cell, they are thermally generated or thermally driven. As long as there is difference in the temperature of the layers of air, then there will be movement of air. Feral cell, however, is mechanically driven by the sinking of the air in the subtropical highs and the rising cell in the polar fronts. At the subtropical belt of high pressure, sinking air, it creates dry and fair weather scenario. Okay, at the intertropical convergence zone, rising air creates thunderstorms and rainy regions. That's why whenever you hear a weather forecast, they are mentioning the intertropical convergence zone. And it's always associated with storms or thunderstorms. Okay, so you now have here the general illustration or the illustration for the general circulation. So the first one would be the simplified circulation or general circulation of the air. But of course, there are other factors which may affect the movement of the air. For example, if there are areas which have larger land masses or larger water surfaces, that could greatly affect the movement of the air. So in reality, we have this more complicated movement or circulation of the air or of the atmosphere. Okay, so next that we are going to discuss would be about monsoons. Take note that when we say monsoon, these are actually seasonal changes in the Earth's global circulation. Now we will focus on Asian monsoons. So let's take a look at this illustration. In the Asia we have here the winter monsoon. This happens if the land mass or the land masses here, particularly in India, we have here a cold temperature. So this happens during winter. We have mentioned that when we compare land and water, during winter or during cold days or colder temperature, the land will be at a colder temperature because the water can retain the thermal energy. So it will be warmer compared to the land masses. Since we have cold air in the land masses, we have there the higher pressure. So the movement is always from higher pressure to lower pressure. So the air will be moving away from the land or away from the continents. It's like we can compare it to land breeze. So coming from the land towards the water, or this time coming from the continents. So it will result to dry air. Okay. Next would be the summer monsoon. Now this time it happens when you have here the land, since it's summer, so the land will be heated at a faster rate compared to the water. So land would be at a higher temperature, so it will be warmer, creating lower pressure area. But in the water, just like the water breeze or the sea breeze, water has lower temperature compared to the land areas. So the movement will now be from higher pressure over the water towards the low pressure area sa land. So that this one carries with it precipitation. So it will not carry dry air, or it will not result to dry air, but it will result to some precipitations or rains. Okay, so that happens during summer monsoons. So take note again that when we say monsoon, this is a seasonal change in the circulation or in the global circulation of the earth. So there, winter monsoon associated, this is for Asia, is associated with winds that blow predominantly off the continents. So it's coming from the continents. And then summer monsoon associated with abundant precipitation over affected land areas because it would be coming from the water surfaces towards the land, so which carries moisture content. Okay, in January also a strong high pressure develops over Asia. Okay, resulting flow of, I already have explained this one. So you can read this one. This is the explanation. Okay, another movement of the air would be the westerlies. So you can see here the pressure gradient force, and then we have the Coriolis force, and then the wind. what happens here in the warm air or in the warm region at the equator, we have mentioned that warm air rises. So we will consider the air aloft or at a higher altitude. That will create higher pressure over the equator, high above the equator. And then for the polar regions, we have mentioned that cold air sinks. So aloft, it is creating a lower pressure area. Therefore, the movement will be from higher pressure above the equator towards the lower pressure area above the polar regions. Okay, so take note that we are considering here the air aloft. And then, it is balanced by the Coriolis force, which is towards the equator. Then, because of that, it will create a wind or westerlies. That the name westerlies would be the wind coming from the west towards the east. Okay, so that is another part of the circulation of the atmosphere. Okay, so I have mentioned before that I can incorporate some of the activities in this video. So what I want you to do now is to summarize the general circulation of the atmosphere using a concept map. So I want you to integrate all the movements or all the air circulation in one concept map. Okay, so that would be your output. All right, that would be the end of our discussion for today. Okay, so next meeting we will be discussing about air masses and also cyclones, right? So complete the activity and submit it. All right, so goodbye everyone.